So today we will be going through question 2.50 in Griffiths Electrodynamics edition 4, and the question gives us a potential V of R, which is a radial dependent potential, radial dependence, A e to the power minus lambda R over R, where A and lambda are constants. So now they're asking us to find the electric field, the charge density, the volume charge density, and the total charge for this given potential. So we know that the electric field is related to the potential by the negative of the gradient of the potential. So now, because the potential only has a radial dependence, so the gradient will just be taking the partial derivative with respect to R of the function A minus lambda R, and now we need to use this is the formula in spherical coordinates. Yeah, and because of the radial dependence, we're ignoring the other factors like the polar and the azimuthal components. And then here we need to apply the single variable calculus quotient rule, and that would give us minus, so let's take it, V into U dash minus U to V dash, then divided by R squared, and then there's R hat. Okay. Yeah, and now we need to just simplify this expression. So that would be R, and then we have the minus A lambda e to the power minus lambda R, and this is minus A e to the power minus lambda R, and that's 1. Partial derivative of R with respect to R is 1, and this is R squared, and there's R hat. And then we can simplify this further. We can take the minus A lambda e to the power, minus A e to the power minus lambda R common and pull it out of the brackets, and we would have A e to the power minus lambda R over R squared times, inside the bracket it would be 1 plus lambda R. Yeah, so yes, and right now, yeah, from here we would have to, oh, there's R hat, yeah, and now this is the electric field associated with this potential, and so from here we need to use the differential form of the Gauss's law, which is the gradient of electric field is equal to the charge density, volume charge density, rho over epsilon naught. But here there are two ways to proceed with the question. One could, again, noting that the electric field only has a radial dependence, and in spherical coordinates, you can see the formula. The gradient, the divergence of E. This is the divergence of E, electric field, like that's how we call it. And the divergence of the electric field with only radial dependence would have this formula in the spherical coordinates, where E sub R is the radial, just the radial component. So basically, it's going to be this one. But and this one, sorry, including this one. Yeah, both of these. So except the r hat. So that's the radial component that needs to be like that would have been used here in order to find gradient dot e of r. But and there's another way. This is the first way. The second way is to take this whole thing again, this thing as a scalar function, and actually we need to use a trick. So let's say that this thing, this electric field, is composed of a scalar function and a vector function v. Let's say this. So a scalar function times a vector function is also equal to this vector function, let's say. And by the multivariable calculus product rule, we have that this will be equal to the gradient of f dotted with v plus the scalar function f times the divergence of the vector function v. So now the one who follows the first way would actually, I mean, it's a pretty common mistake here. Someone would obviously try to follow the first method because it comes to, the quick into our minds when we see this problem. But then it's actually the wrong method here, because doing this method, the first method, would actually, we are just ignoring the fact that the electric field blows up when r equals 0. When r equals 0, this electric field is not defined. So simply taking its partial derivative this way, the gradient dot the del operator dot e, which is also known as the divergence of the electric field. We are actually ignoring the fact that at r equals 0, this thing is not defined, and this will give us some function which is actually right, but then that function only obeys the rule except at the point where r is not equal to 0. But at the point r equals 0, this thing doesn't work. The first formula doesn't work. We shouldn't be using that, and hence we should go with the second method, because the second method actually will lead us to something known as the Dirac three-dimensional Dirac delta function, which overcomes the difficulty, or not difficulty, like the mathematical issue of the electric field blowing up at r equals 0. It kind of overcomes that stuff. That's why the function was built in. So we should, so this comes with practice, and someone who does a lot of practice will obviously go with the second method when they see questions where there is a 1 over r square dependence. I mean, there's a 1 over r dependence or whatever, where r is in the denominator, but it blows up. So you shouldn't be following the first method, and instead just go with the second method. And now moving on with the second method, let's start with the first part. Let's say that it's, so we need to choose now, because we're only following the second method, we need to choose our scalar function f and the vector function v. This is also a trick. Like, we have to be careful when choosing what to take our vector function, what to take the scalar function. So one who does, and as I already gave you the hint that we will be going, we'll be using the Dirac delta function. One would evidently choose the scalar function f from the electric field to be equal to a e power minus lambda r times 1 plus lambda r, and the vector function v to be r hat over r squared. Now this choice of scalar function f and v is just to it's just a practice, and kind of in order to get in the Dirac delta function, which will actually solve this problem, and you will see as we move on. So let's start with the gradient of f in this case, which is again a radial dependent function. So it will be simply taking the derivative, partial derivative, with respect to r of the stuff here. And now we need to use the single variable calculus. Now we need to use the single variable calculus product rule, which is, just take times the partial derivative of E minus lambda r. Yeah. So this is e to the power minus lambda r, and we have got here right now. Yeah, that's done. And then times r. Oh, sorry, there's a lambda here. The partial derivative of this thing gives us a lambda, and the stuff here 1 plus lambda r times the partial derivative here again gives us a minus a lambda e to the power minus lambda r. Now again we can take the a e to the power minus lambda r common. Actually, we can also pull out the lambda. Okay, just a second. A lambda e to the power minus lambda r. That would be 1 minus 1 plus lambda r, which is a lambda e to the power minus lambda r times minus lambda r. That's minus a lambda square e to the power minus lambda r, and there's an r here. Okay, just to not make the notation confusing, I'll put the r ahead. Minus a lambda square r minus lambda r. Okay, yes. So this is the gradient of the scalar function in this form, and now let's proceed with. Okay, now we need to. Now from this, after finding the gradient of the scalar function, we do dot it with the vector function, and yes. So again, because it's the only radial component, so we just took the radial the derivative with respect to r, and we need to use the r hat as usual. And now because the gradient of a scalar function is a vector, and now the gradient of f dotted with the vector function v would simply be minus a lambda square r minus lambda r dotted. No, there's an r hat. Okay. Dotted with the function r hat over r square, and now because we see that it's r hat and r hat, so the dot gives you a 1, so we simply multiply these, and this would be minus a lambda square minus lambda r divided by r. Yeah, because the dot just gives us 1. I mean r dot r is 1, and then we have r square and r in the numerator and r square in the denominator, so that cancels out, and we have an r at the denominator now, and this simplifies to this expression. So, and now moving on to the next part of the formulation, which is actually taking this stuff here. Now let's calculate the gradient of the vector function, and sorry, not the gradient, the divergence of the vector function, and this is divergence of the vector function. So now this is where the Dirac delta function comes into play, and so now our vector function was chosen to be, as you all had seen, we had chosen this to be our vector function. So now that's r hat over r squared, and the gradient of this function, sorry, the divergence, okay, the divergence of this vector function is actually 4 pi del cube of r, where this stuff is the 3-dimensional delta Dirac function, and this actually comes from the result of the known as the divergence, the paradox of the divergence theorem. I mean, there's a divergence theorem paradox in the Griffiths book if you go through it. So this is where that result comes in, I mean the gradient of this the divergence of this vector function is actually 4 pi del cube of r, and then we need to take the product of the scalar function f and the divergence of the vector function, which is actually so now what was the scalar function was a e minus lambda r, a to the power minus lambda r times 1 plus lambda r, and now that it's a simple product, there's no dot and stuff. This is 4 pi del cube of r. Okay, and now this would be 4 pi a e to the power minus lambda r. Okay, and then we have the 4 pi a e to the power minus lambda r. We have the 1 plus lambda r minus lambda r, and then the del cube of r. So this is the three-dimensional delta Dirac function that I was talking about, and now there's a special property of the Dirac delta function. This is the three-dimensional delta Dirac function. So there's a special property that, let's say this is a function of r, and then this is a function of r. So basically this would simply be equal to this, because the Dirac delta function is 0 everywhere except at the point r equals 0 for this one, because here I have, if I had taken something like r minus r prime for this, then it would have been 0 everywhere. The function would have been 0 everywhere except at the point r equals r prime, where it would have a sharp spike. Yeah, so something like this. So like just say this is the axis, and then this goes, and then the sharp spike, a thin spike, and then the 0 again. So that's how the Dirac delta function is defined. And so wait a second. Yeah. So what I was talking about is like it's 0 here, there's a sharp spike, a thin spike, and then there's 0 again. And this is like the point r prime. In this case, r prime equals 0. So it's the function, the Dirac delta function is 0 everywhere except at the point r equals 0 in this case, and that's where they have a sharp spike. So this whole thing would be 0 throughout except at the point r equals 0. So it's simply equal to f. Thus we can conclude that it's equal to f of 0 times, again, del cube, the three-dimensional delta Dirac function. That's the reasoning. So this is a property, and because let's say this is another, to just not confuse you with the notation, let's say this is some function f prime that I was talking about, because I have already used f before. So yeah, and now here f prime is equal to 4 pi a times e to the power minus lambda r plus lambda r. So whatever's there in front of this this thing here, whatever's there in front of the Dirac three-dimensional delta Dirac function, and now let's say so now when r equals 0, this thing is simply 4 pi, because e to the power 0 is 1, and 1 plus 0 again here is 1, so it's simply 4 pi a. Sorry, it's 4 pi a. And so the divergence of this electric field reduces to minus a lambda square minus lambda r over r plus 4 pi a del cube of r. Okay. Now, yeah. So now we know again, like we just need to find the volume charge density rho from here, which is simply rho equals epsilon times 4 pi a del cube of r, three-dimensional delta function, minus a lambda squared minus lambda r over r. So this is the volume charge density that's associated with this potential and hence the electric field. And we found the electric field, we found the charge density associated with the potential. And now the final thing we need to find is the total charge Q. Now to find the total charge Q, we need to integrate the volume charge density rho of r over the volume element d tau prime, let's say. Let's just keep the notation simple. Let's just use d tau equals charge, total charge enclosed Q. And because we are not given a specific shape to integrate over the volume, we need to take the limits of the integration over the whole space. And so let's do that. Okay, so let's take the epsilon out of the integral because it's anyways a common thing, constant, and there's a 4 pi a del cube of r d tau minus the integral a lambda squared. Okay, so it's actually, let's move this a bit aside. Okay, yeah, and then we have a lambda squared e to the power minus lambda r over r, and then there's a d tau here. Okay, so now the first integral again. Now let's do the first integral, this one. So we know that by fact, this is the definition of the Dirac delta function, is if you integrate it over all space. So yeah, I forgot to mention an important thing. This integration is over all space. This integration is over all space, and this one too. All space meaning like throughout the coordinate system. Yeah, so all space, this will basically be equal to 1. So the first integral simply evaluates to, let's forget the epsilon, not for now. So the first integral simply evaluates to, like, let's say this, 4 pi a del cube of r d tau is actually equal to 4 pi a. Simply 4 pi a, because this whole 4 pi is a constant, we put it out, and then del cube of r d tau is simply equal to 1 over all space. So we have this as 4 pi a. Now the second integral, we actually need to use the spherical coordinates in order to solve the integral. So we will have from 0 to 2 pi, and then another integral from 0 to pi. So these are just computations that we need to do, and this is from 0 to r, infinity, I believe. And because it's integrating over all space, so these are the limits over all space in spherical coordinates. And then this is a lambda square minus lambda r over r, and then the d tau in spherical coordinates simply becomes r squared sine theta dr d theta d phi. So yeah, and phi and theta are, I'm using the same definitions as defined in the Griffiths book. And yeah, so the limits of integration of 0 to 2 pi are for the d phi, and then this 0 to pi is for the sine of theta d theta, and the last integration from 0 to infinity is for, simplify this expression, a lambda square simplifies to r minus lambda r dr. So yes, and now I need to, so the first one is simply 2 pi, the second one is 2, because I mean integral of sine theta d theta would give us a minus cos theta, and then taking the limits from 0 to pi would give us a 2. And now in order to solve the third integral here, this one, just pull out the constants a lambda square outside of the integral, and then the integral 0 to infinity of r minus lambda r dr, we can actually use the single variable calculus integration by parts to find that this integral evaluates to 1 over lambda squared. And I won't be going through the integral right now because it's going to make the video too long, but I might do it some other time, and might put up the video about it. So just keep a lookout. And now this is basically 1 over lambda squared times 1 over lambda squared. The lambda squares cancel out, and we have 4 pi a. Yeah, so we have 2 pi times 2 is 4 pi, and that's it. Yeah, and now just going back to this integral here, which is actually equal to q, which comes from here, we'll actually just simply evaluate to q is equal to epsilon naught. The first one, the first integral in the line here was equal to 4 pi a, so we're going to have 4 pi a, and then we have to subtract with this integral, which also evaluates to 4 pi a, as we see here. And so that's simply subtraction, and so this is now equal to 0. So the total charge enclosed in this in all space related with this potential is actually equal to 0, and that solves our problem. We found the electric field and the charge density and the total charge related to this potential.